So when we take, let's say, a simple thin hollow tube, and subject it to torsion, this is going to go through a twisting action, right? And what we figured was, by looking at the twisting, we figured that there are some strains, just like what we did here. We figured out that as far as epsilon ij is concerned, there was only gamma x is here. So gamma 1, 2 or gamma 1, 3 are present. Okay, this is what we arrived at. Okay. For example, if I take like this, or if I take like this, depending on what is y direction and z direction, we would get either 1, 3 or 1, 2. When I say 1, 2 here, it also means 2, 1, right? All the other strains were 0. Okay, so it renders a special case. Once I have a special case, it is possible for me to write down all those equations that we wrote down earlier, with related to equilibrium, related to I'm not an old winding record. Related to, you can stop it. One is related to equilibrium. The other I can write related to, what are the other things I can write? For example, in this, elongation is what we are relating to, right? Elongation. And using elongation, we wrote down strain. Using strain, we wrote down what is stress. This elongation to strain, what did we use? Elongation to strain, what did we use? I'm asking a very simple question. Out of the 3 sets of equations that we wrote, how did we relate epsilon and displacement? Geometry of deformation, correct, but we used those equations and called them as what displacement equations? What displacement equations? Strain displacement equations. So strain displacement equations give me what are strains in terms of displacement. And how do I connect these two? How do I connect these two? Given epsilon 1, 1, how do I find out this? What do I use? What do I use? Come on, yaar, come on.
Stress strain relations.
Stress strain relations or constitutive equations, right? So indirectly, all those equations that we listed, we are using here in this special condition. Okay, and similar is the exercise that we resorted to as far as this is concerned. Just like what we have here, where u is the displacement or the elongation that we are looking at. In this case, we are looking at angle of twist. So angle of twist was the first quantity that we looked at. From the angle of twist, what did we get? What did we obtain? Go ahead. Voices, please. From the angle of twist, what did we get? Just like from displacement, we got something. From angle of twist, what did we get?
Twisting moment.
No. From angle of twist, I should have gotten something, no? Angle of displacement is similar to the displacement u, right? For a bar.
Strain.
Strain. What strain in this? The shear strain,
Shear
right?
strain.
Right. Shear strain. And from shear strain, so this is strain displacement
Stress.
relations. From shear strain to shear stress. And to find this relationship, I used stress strain relations. Okay. Why did I use equilibrium equation? Why did we use so strain displacement relation we used, stress strain relation we used. We started with angle of twist, which is the reduced form of the displacement, right? But where is equilibrium here? Where is equilibrium that I have to use? I have to use equilibrium also, no? I've used strain displacement, I have used the strain, but where is equilibrium? What does equilibrium equation give me? What does equilibrium equation relate to? What does it connect? What are the quantities it connects? Lot of questions,
Forces.
but only one answer. Yeah?
Forces.
Forces. Here, what is the force?
Torque.
Torque. And therefore, through equilibrium makes sure that in inner internal quantities are equal to external quantities, and therefore I get a relationship with torque. Okay. Of course, I can go either way. I can start with torque and go to angular twist, or I can start with the angle of twist and go to torque. This is what we did. Can you just tell me what all we did for torque here? The twisting here. Angle of twist, we said theta, and if there is a length involved here, theta, I mean L, then theta by L should be equal to, do you remember?
T by
Ah,
jg.
that is the final. Only this strain displacement relation. Theta is the displacement, right? Rotational displacement. Theta by L was equal to, I need to relate to shear strain. Do you remember what we did here? We said, okay, this is the theta. This is the theta, and we said the strain is like this. This is strain, gamma. Gamma times L should be equal to R times theta, because this total length that I have is the same, correct? This is what we did, right? Or in other words, theta by L was equal to gamma by R. All right? Or I can write this to be gamma is equal to R theta by L. And we said, okay, by reducing this length to a small length, this theta also keeps reducing, as you can see here. Though this angle remains the same, the theta, which is the rotation between two cross sections, keeps reducing. So I can put a d theta here and dl here, so that I now have gamma is equal to R times theta comma x, because this is the x direction, right? So this is what I got out of this whole thing. Correct? And then I resort to shear strain to shear stress relationship. And how did I do that? That was very simple. So let me write it over here. So in this stress strain relationship, all I had to look at was what is it that gamma will that gamma as strain would produce in terms of stress. There is only one stress that it would produce, which is tau, and tau is equal to G, which is the modulus of rigidity. We also knew that this was equal to E by 2 into 1 plus mu, G times gamma, right? And that's all. That's the stress-strain relationship we got. And then what did we do? We adopted equilibrium in order to connect to torque. Is this clear to you now? Right? We started with angle of twist. We found out shear strain out of it. Just like what I did for the axial deformation. From U, I found out strain in this case to be epsilon 1 was equal to for the rod for the axial deformation, epsilon 1 was equal to theta or alpha, it doesn't matter. I've just used theta over here. If you like alpha, that's perfectly all right. I'll change it to alpha here. Okay. All right. In this case, a similar thing that I did was epsilon 1 was equal to dou u by dou x. You remember u comma x, right? This was the relationship, which was stress strain relationship. And once I got this, then I used E times epsilon 1 to be equal to sigma 1, right? And then from the stress, equilibrium connects to the external force, right? Which is sigma times A is equal to F, right? Sigma times the area is equal to F. Is how I did for an axial problem. For the shear problem, I used this angle of twist, started with angle of twist, and then used that to find out what would be the gamma. Here we experimented with what happened when I twisted, right? Again, I'm not able to see it. No? I don't know why. Very good. We experimented in this and figured out that it is only gamma that I will see here as a change in angle. Use that information in order to obtain a relationship between angle of twist and strain. From shear strain, I went ahead with shear stress and then the torque. Do you remember the torque? Now you tell me, was it Megha who was answering earlier?
Yes, sir.
What was it?
Theta is equals to
You're
TL
going,
by
so theta, so there are relationships that I got. First relation should be between shear stress and torque. Shear stress and torque is, do you remember? T, do you remember? TR by J, right? And then we also have gamma is equal to, what would be gamma? I have to divide by G, TR by, am I right? Yes or no?
Yes, sir.
Gamma is that?
GJ.
Is this correct?
Yes, sir.
Okay. Gamma is
GJs.
by GJ. Is this correct? Is this correct?
Yes, sir.
All right. And what was theta?
Theta is equals to TL by GJs.
GJ. Very good. Right. We also said, okay, TL by DJ can be is very similar to a flay, right? Where we replace uh, E by G
Yes.
and A by J, L remains the same, F by T, right? So that we can get this relationship, okay? So instead of delta is equal to F L by EA, we can replace these by appropriate quantities to get this. So there is a similarity or analogy that we see between these two. So far so good. Very simple, absolutely no problem. This is for a rod with only end torque, because we separated that, integrated theta comma x. Oh, I'm sorry, I'll use alpha here. We integrated alpha comma x in order to get alpha by L, right? And that's how I got this L here. Okay, because T is a constant, the torque is a constant. Okay, as simple as this. What did I find this out for? I found this out for a hollow thin tube. Very important to know. Okay, I looked at a hollow thin tube of this sort, hollow thin tube, twisted, right, and figured that this is the relationship I will get. So far, okay. Is this clear? Any questions? Any questions? Sir, we took alpha. I've answered that question quickly. One or two questions if you have. Have a look at this. This is going to be the pattern all the time. Even if I take bending, I will do a very similar thing. I figure out what is this to start with, and then go down in terms of using those relationships. Okay. All right. Let's see one question if you have. Remember, in this case, which, okay, sir, how are we calculating J here? Okay, J here is the, if I have a thickness over here as T, right, we figured out that J was equal to 2 pi R cube, right? This is what we used, we got. And that's how we substituted for J here. Do you remember? When we do the integration, when we do the integration, because let me just quickly draw that. Shall I erase this? If I have the cross section and there is a thickness over here, we figured that the shear stress is acting like this. Okay. This shear stress contributes to the resistance to the torque that is applied. The torque that is applied, right? These two, this is internal shear that is arising out of the torque that has been applied outside, correct? Externally, right? Which means that if I take moment about this torque should be equal to the resultant of all the shear stresses put together, right? And given that this is equal to T and this is R, it is now possible for me to find out the integral tau times the area, which is 2 pi R T times, so this is the area, this is the lever arm, correct? Why should I integrate? I don't have to integrate. 2 pi R times T times R. Have I missed out anything here? Have I missed out? This should be equal to T, right? Now, this can be written as R cube and then one R can be taken out. That's how I get this TR by J. Okay, is this clear? Is this clear? Yeah. Any other doubt? Now, I have a 2 mark question. Ready? No answer. You can get 2 marks out of answering this question.
Ready, sir.
Ready? All right. Okay, ready. What did we solve for? We solved for a thin, hollow tube. Okay. But now I want to find out for the cross section, which is a solid cross section. This is a hollow cross section, right? After finding all this out, I want to now find out for a solid cross section. Given that I have derived for this, I need to derive for a solid cross section. Let me take like this. Each is a dr, and then sum all of them up, right? That's how I got integration, correct? Right? If I take each one of this is dr, and I sum up infinitely, I should be able to get for this. When do I sum? When do I add? When do I add? And what do I add?
A solid cylinder is a summation of hollow cylinders. Right?
Summation of hollow cylinders.
Yes, they all are like.
Because correct, because displacement should be added. No, they are coaxial. Okay, they are coaxial. Correct, Ayush. But what is it that connects them all? Displacement should not be added, by the way. What? Supposing I take a cylinder of length L or a tube of length L, right? And I looked at the end twist. What should I look at as far as this is concerned? A solid tube. I cannot call it a tube, so solid cylinder, and the end which is twisted by an extent, correct? So, and therefore, what do you know about the individual tubes here that you're summing up? Theta should be the same for all. Fantastic, Bindu. Correct. The end displacement is the same. Do you remember when I have two rods and the end displacement is the same, then I sum the two to get the stiffness, right? So if I get the stiffness for each one of them, I can add the stiffness for all of them put together, correct? What is stiffness here in this? How do I figure out stiffness? What is the torque needed for
Unit twist.
unit twist? Similar to what is the force needed for a unit displacement, right? And in this case, it is G J by L. L is the same for all of them. G is the same for all of them. J alone is different for each one of them. Correct? Right? So if I have to add all the stiffnesses, I want you to do this working in the class. I need to now add all the stiffnesses. So summation, right? Summation, help me out here. G I can take out, right? L I can take out. Go ahead. So let's say this is K, okay? G I can take out. Go ahead. Analog to stiffness. Yes, yeah. This is so G by L, and this is summation of J I. Okay, I is the number of them. So this is one way of writing, right? The other way of writing is integrating, right? Help me out in integration now. I should integrate from the smallest tube to the largest tube, and therefore here
0.
0
R
to R
2 pi R
2 pi R
dt thickness T
dr. Okay,
dt
dr.
into R.
So 2 pi R
That's good.
dr is nothing but area
Area
times
in R square.
R square. I have to integrate. Is it not? So simple, right? So remember we derived for a hollow cube. Now I can find out for a solid cross section by simply integrating, right? All the rest of this formula are the same, right? How do I find out alpha? Alpha is nothing but T by stiffness K, correct? So K I have already found out. I can insert it and get alpha, right? From alpha, it is possible for me to get all the other terms that we are looking at here. Here, if I substitute for this J instead of the other J, I should get all the results over here. So simple, right? But not all the time I will have a circular cross section. Okay, and there are certain amendments that I have to do if it is not a circular cross section. I'll come back to it later. Is this clear to you? Yeah. So let's just look at some of the scenarios before we stop today. Okay. Supposing I have something like this, okay, and it is subjected to and I want to find out how much of twist has happened at the end of this. How will I go about solving this? Let's just figure out how we solve for different structures, having found out these basic ideas. How will I do it? Let's say this is
Effective
L1,
K.
this is L1, this is L2, fantastic. Effective K. K effective I'll find out, right? What is K effective here?
By K effective is equal to 1 by K1 plus 1 by K2.
And what is K1? If this radius is, if this diameter is D1 and this diameter is D2, I can find out J2, J1, right? Gj by L, Gj by L1 will give me for K1, Gj2 by L2 will give me K2, from which I can find out K effective. Once I find out K effective, then alpha at the end is equal to
Tau by K.
but the problem is there is T2 here and T1 here. So what shall I do? I cannot do like this, correct? Yes or no? I cannot do like this. Give me another way of doing this. Give me another way. Quickly. What do? I draw what diagram?
Twisting moment diagram.
Twisting moment diagram. I should draw the twisting moment diagram. Find out the twisting moment in this and twisting moment in this before I use, and therefore when I find out the twisting moment in this, and therefore the alpha that this is subjected to, that this goes through, and the alpha that it goes through, then I can add the two twists to get the total twist.